paper of the day is Hive, a petabyte scale data warehouse using Hadoop. This paper presents Hive, an open source data warehousing solution built on top of Hadoop. Hive supports queries expressed in a SQL-like declarative language, HiveQL, which are compiled into MapReduce jobs that are executed using Hadoop. In addition, HiveQL enables users to plug in custom MapReduce scripts into the queries. The language includes a type system which supports for tables containing primitive types, collections like arrays and maps, and nested compositions of the same. The underlying IO libraries can be extended to query data in custom formats. Hive also includes a system catalog, metastore, that contains schemas and statistics which are useful in data exploration, query optimization, and query compilation. In Facebook, the Hive warehouse contains tens of thousands of tables and stores over 700 TB of data and is being used very extensively for both reporting and ad hoc analysis by more than 200 users per month. Now let's look at the data model, type system, and query language for Hive. Similar to traditional databases, Hive stores data in tables, where each table consists of number of rows and each row consists of a specified number of columns. Each column has an associated type. The type is either a primitive or a complex type. It supports all major primitive types: integer, floats, doubles, and strings, as well as complex types such as map, lists, and structs. The Hive query language, aka HiveQL, comprises of a subset of SQL and some extensions that they have found useful in their environment. While the tables are logical data units in Hive, table metadata associates the data in a table to SDFS directories. The primary data units and their mappings in the SDFS namespace are as follows. Tables. It's a table. A table is stored in a directory in SDFS. Partitions. A partition of the table is stored in a subdirectory within a table's directory. And buckets, where a bucket is stored in a file within the partitions or the table's directory, depending on whether the table is partitioned or not. Hive can take an implementation of the Certi Java interface provided by the user and associate it to a table or partition. As a result, custom data formats can easily be interpreted and queried from. The default Certi implementation in Hive is called lazy Certi. It deserializes rows into internal objects lazily so that the cost of deserialization of a column is incurred only if the column of the row is needed in some query expression. Hadoop files can be stored in different formats. A file format in Hadoop specifies how records are stored in a file. Text files, for example, are stored in text input format, and binary files can be stored as a sequence file input format. Users can also implement their own file formats. Hive does not impose any restriction on the type of the file input formats and the data is stored in. The format can be specified when the table is created. Hive building blocks. The following components are the main building blocks in Hive. Metastore, the component that stores the system catalog and metadata about tables, columns, partitions, etc. Driver, the component that manages the lifecycle of a HiveQL statements as it moves through Hive. The driver also maintains a session handle and any session statistic. Query compiler, the component that compiles HiveQL into a directed acyclic graph of MapReduce tasks. Execution engine, the component that executes the task produced by the compiler in proper dependency order. The execution engine interacts with the underlying Hadoop instance. Next is Hive server, the component that provides a thrift interface and JDBC, ODBC server and provides a way of integrating Hive with other applications. Clients components like CLI, the web UI, and JDBC, ODBC driver. Extensibility interface, which includes Certi and object inspector interfaces, already described previously, as well as the UDF, that is user-defined function, and UDAF, user-defined aggregate function interface, that enables users to define their own custom functions. In preliminary experiments, they improved the performance of Hadoop itself by 20%. The improvements involve using faster Hadoop data structures to process the data, for example, using text instead of a string. The same queries expressed easily in HiveQL had around 20% overhead compared to optimized Hadoop implementation. Hive's performance is on par with the Hadoop code. They also run the industry standard decision support benchmark DPCH. Now let's look at the contribution. Hive was very popular with all the users within Facebook. Today, they regularly run thousands of jobs on Hadoop Hive cluster with hundreds of users for a wide variety of applications, starting from simple summarization jobs to business intelligence, machine learning applications, and to also support Facebook product features. Now, let's talk PS score for this paper. Overall, this paper is a decent read, so it gets 9 out of 10 on readability. With 10 pages long, it scores 9 out of 10 on length. It's an analysis of an existing production system with pretty good description, so that makes it 9 out of 10. Its industry value and learning meter is pretty high, so it gets 10 out of 10 on each. Overall PS score is 9 out of 10.